Welcome to the first part of lecture 19 on graph theory. In this lecture, we will talk about edge coloring. So, like vertex coloring, in the edge coloring we will color the edges of the graph in such a way that no two adjacent edges have the same color. And of course, the optimization problem again is we need to color the edges with minimum number of colors. So, I will start with formal definition of edge coloring. So, a graph G is k edge colorable if its edges can be colored with k colors so that no two edges have the same color. Right. So, let me give an example of a graph and it edge coloring. So, I will consider this graph again. Now, we need to color the edges, right, so that no two adjacent edges, have the same color. So, by adjacent edges means these two edges are adjacent edges. So, they will get different color. Let me color this edge say red and okay. So, I colored this edge red, then I can't color this edge by red color. I can color this edge by red color. Okay. And of course, there was an edge here. Now, I color this edge by blue color and this edge also by blue color. I am not removing the black thing, and so they are not two adjacent edges. Let me color this edge and this edge by green colors. So, and these two edges are left, so they can be colored with say yellow colors. Okay. So, I have colored this graph with 4 colors and no two adjacent edges have the same color. So, this graph G is 4 edge colorable. Okay. Of course, the optimization problem is to is to color the edges of the graph with minimum number of colors. Now, we will see whether we can color this particular graph with less number of colors than 4 color. So, at this moment we have used 4 color. The question is whether we can color this graph with less than 4 colors. Okay. If G is k edge colorable, but not k minus 1 edge colorable, then we say that the chromatic index of G denoted by chi prime G is equal to k. Now, it is an easy observation. So, this is the chromatic index denotes the minimum number of colors required to edge color a graph. Now, since edges sharing and end vertex need different colors, so chi prime G, the chromatic index of a graph G is always greater than equal to delta G. Delta G is the maximum degree of the graph G. So, here you can see that this node has highest degree. Of course, this node is also having highest degree, that is 4. So, let me label this node as A, B, C, D and E. So, look at node A, it has 4 edges. Four edges are incident to this vertex A, and so this edges are adjacent edges. So, we have to give different colors to all these 4 edges. That is why the chromatic index of this graph will be at least the degree of this vertex, which is of course, the highest degree. So, this is a lower bound for the chromatic index, and here we can see that we can color G with 4 colors, which is the lower bound. That is why the graph G has chromatic index 4. I hope that this is clear to you. Next, we talk about a theorem which gives the upper bound on chromatic index. This is due to Beijing and Gupta in 1964. It says that if G is a simple graph, then chi prime G is less than equal to delta G plus 1. That means the maximum number of colors required to edge color a graph is delta g plus 1, maximum degree plus 1. And just now we have observed that the lower bound for chi prime g is delta g. This is the minimum number of colors required to edge color a graph, and this theorem says that the upper bound is delta g plus 1. So, chromatic index will take value either delta g or delta g plus 1. Okay. So, hence chromatic index of a graph is either delta g or delta g plus 1, right. Now, we will classify the graphs into two classes. Class 1. So, a graph is in the class 1 if the chromatic index of that graph is equal to delta g, and a graph is in class 2 if the chromatic index of the graph is equal to delta g plus 1. So, what we have observed is that the chromatic index of a graph can be either delta g or delta g plus 1. So, on the basis of this one, we classify the graphs into two classes. Class 1 if the graph has a chromatic index delta g, and class 2 if the graph has chromatic index delta g plus 1. Now, there is a theorem due to Erdos and Wilson. Let G n be the set of graphs of order n. Order n means the number of vertices is equal to n, and G n prime is set of graphs of order n and of class 1. Okay. Then the number of graphs of order n and of class 1, that is cardinality of this set, by the number of graphs of order n. This ratio tends to 1 as n tends to infinity. Okay. So, the meaning of this one is that almost every graph, very powerful theorem, that almost every graph is of class 1. That means, you pick a graph of order n and it is highly probable that it will be of chromatic index delta g, right. So, most of the graph can be colored with delta g, edge color with delta g colors. Okay. So, I give some examples of graphs which are in class 1 and class 2. So, regular graphs of odd orders. Okay. So, regular means every vertex has the same degree, and odd order means it will have odd number of vertices. So, this is a small example of a regular, it is a 2 regular graph, because every vertex has degree 2 and it has odd number of vertices. So, this is a 2 regular graph with 3 vertices. And what is the chromatic index of this graph? So, if I color this edge by red color, I can't use red color for this edge or for this edge. I have to use a different color for this edge, say green color. If I use green for this one and red for this edge, then I can't use red or green for this edge. I have to use a different color. So, let me use a blue color. So, we can see that the chromatic index of this graph chi prime g is equal to 3, and you see that the delta g is equal to, the maximum degree is equal to 2. So, for this graph chi prime g is equal to delta g plus 1. So, regular graphs of order of odd order are class 2 graphs. This is true. You can pick any regular graph of odd order, they are of class 2 graph. And the other example of this is for, say, bipartite graph. Bipartite graph. It says that every bipartite graph is of class, here is the theorem. This is due to Koenigs. (1916) that if G is bipartite, then chi prime G is delta G. So, this theorem will prove that every bipartite graph is of class 1. So, here is the proof. This is an interesting result. So, G is a bipartite graph. So, G can be embedded into delta regular bipartite graph. By adding dummy variables, dummy vertices and edges. Okay, so what I mean by this one is that you are given an arbitrary bipartite graph and it can be embedded into delta regular bipartite graph. So, suppose you are given this graph, for example, this bipartite graph. So, and the edges of these graphs are this edge, this edge, this edge, and this edge. Okay, sorry. So, this is the graph, that is bipartite graph that you are given initially. Now, this bipartite graph has maximum degree delta G equal to 2. So, what it says that this graph can be embedded into delta regular bipartite graph. That means, you can convert it to 2 regular bipartite graph by adding new vertices and edges. So, you add a new vertex, say this one, and you add new edge. So, this is a new edge which you are adding to make the graph 2 regular bipartite graph, and this is another new edge. Now, you can see that this graph has become 2 regular, this has become delta regular bipartite graph. Right. So, you can always embed a bipartite graph into delta regular bipartite graph by adding dummy variables, dummy vertices and dummy edges. Then we show that every delta regular bipartite graph is delta edge colorable. Okay. So, G is delta regular bipartite graph, and we know that if a graph is delta regular or k regular, then the Hall's condition is satisfied and the graph has a perfect matching. So, that we have done in the during our matching classes. So, this graph, since it is a delta regular graph, so G has a perfect matching. Right. So, I can show that okay, this graph has a perfect matching. So, one perfect matching is this one, simply this one. Right. So, this is one perfect matching. So, now you color all the edges of this matching with one color. You can do that because matching is a collection of disjoint edges. So, you can color them with the same color, all these edges you can color red. That means, you are coloring this edge red, this edge red and this edge red. And then what you do is that you remove the edges of perfect matching from G to obtain delta minus 1 regular bipartite graph. And repeat this process. So, once you have a perfect matching for the delta regular bipartite graph, you remove that perfect matching from the graph and then you will get a delta minus 1 regular bipartite graph, and delta minus 1 regular bipartite graph has again a perfect matching. You get a perfect matching, you color all the edges of that perfect matching by one color, and you just repeat this process, say delta minus 1 time. So, here you can see the graph was initially 2 regular bipartite graph, and once you remove these edges from this one, from this graph G, you will get one regular bipartite graph. So, you will be left with this graph. Once you remove these edges from this graph, you will be left with this graph, which is one regular. So, this itself is a perfect matching. So, you color all this all the edges of this graph with one color. So, in the original graph, you are coloring this edge by blue, this edge by blue, and this edge by blue, right. So, you can see that you can, in this way you can color delta regular bipartite graph by delta colors. So, that is why if G is a bipartite graph, its chromatic index is delta G. So, this proves that every bipartite graph is of class 1. Thank you very much.